All right, so we know what an atom looks like. We also know what the nucleus of an atom is like from studying the radiation that comes out of it. We are also starting to understand the power and beauty of the periodic table of elements. However, most of the time, out there in the real world, we don't find atoms in their pure elemental forms, and the interactions that cause atoms to combine have nothing to do with the nucleus. So the next logical step would be to spend some time discussing the combining of atoms and exactly why atoms of elements combine in the first place. When atoms combine, they form molecules and compounds. Outside of a science classroom, these two terms are used synonymously, but in chemistry class, there is an oh so slight difference between the two terms. Molecules are two or more atoms held together by chemical bonds. Some sources will be even more specific and say a covalent bond. So that means these substances, ozone, oxygen gas, nitrogen gas, hydrogen gas, methane, ammonia, and water, are all molecules. Seems easy enough. Compounds are substances composed of two or more different elements joined by chemical bonds. It seems the only difference between the two terms is the word different. Following this definition then, water, ammonia, and methane would be considered compounds. Each of these substances has two different elements bonded together. These substances also fit the definition of a molecule. So water, ammonia, and methane can be considered molecules and compounds. However, ozone, O2, N2, and H2 are not composed of two different elements bonded together. So they can only be classified as molecules. Whew! We will continue to discuss the difference in more detail, but for right now, just understand that compounds can be considered molecules, but not all molecules are compounds. When atoms of elements combine, they form chemical bonds. Chemical bonds are attractive forces between atoms or ions. These attractive forces can come from a transfer of electrons, which is how an ionic bond forms, or a sharing of electrons, which is how covalent and metallic bonds form. As we begin our discussion of the various types of chemical bonds, we will try to model what is happening by using what is called an electron dot diagram. An electron dot diagram is a way of representing the valence electrons of an atom by placing dots, which represent the valence electrons, around the element symbol. Let's talk details. Atoms form chemical bonds in an effort to achieve an outer energy level full of electrons. You will hear me refer to the outermost energy level as the valence shell or valence energy level, because that's where the valence electrons can be found. For 116 of the 118 types of atoms, a full outer energy level equals 8 electrons. This is what's known as the octet rule. The two exceptions are hydrogen and helium atoms. These atoms only have one small energy level around their nuclei, and this first energy level can only hold 2 electrons. Hydrogen and helium atoms follow what is known as the duet rule. By the end of this unit, we will discuss how valence electrons behave to form 3 different types of bonds: ionic bonds, covalent bonds, and metallic bonds. For now, let's focus on electron dot structures, which will help us model the different types of bonding. We will start by using electron dot structures to explain why the noble gases are so unreactive. The noble gases are helium, neon, argon, krypton, xenon, and radon. Now, how many electrons does an atom of each noble gas contain? You remember that atoms are neutral, right? That means the number of positively charged protons equals the number of negatively charged electrons. So by looking at our periodic table, we should know that the atomic number, which tells us the number of protons in the nucleus, also tells us the number of electrons in the neutral atom. Therefore, hydrogen has 2 electrons, neon has 10, argon has 18, 36 for krypton, 54 for xenon, and finally radon has 86 electrons. Okay, well, how many of these electrons are valence electrons? Remember, valence electrons are electrons in the outermost energy level, the valence shell. All the noble gases will have 8 valence electrons except helium. Helium only has 2 electrons to begin with. Remember, helium follows the duet rule. Okay, how do I represent these valence electrons in an electron dot structure? First, you write the symbol of the element. He in this case. Then you use dots to represent the electrons. For helium, you would put 2 dots around the symbol. You can see I put those 2 dots on the left side of the symbol, but I could have put them on the right side, or below the symbol, or even above the symbol. It doesn't matter as long as you have 2 dots representing helium's 2 valence electrons. An atom of neon would have 8 valence electrons. I can see this by looking at my labeled periodic table. Start by writing the symbol for neon. Then start putting dots around the symbol. Please follow this next rule for every element except helium. You put a dot on each side of the symbol before you start pairing up dots. The most dots you can have on any side of a symbol is 2. For example, putting 4 dots above the symbol and 4 dots below the symbol is unacceptable. So the electron dot structure for neon would be the symbol for neon with 2 dots on each side of the symbol. How about argon? Well, it's a noble gas, so an atom of argon has 8 valence electrons. Write the symbol Ar and start placing dots, 1 on each side before doubling up. The electron dot structure for argon looks exactly like neon's. I think you will start to see a trend here. Krypton has 8 valence electrons because it's a noble gas. The electron dot structure will be the symbol, Kr, surrounded by 8 dots, a pair on each side of the symbol. Xenon is a noble gas. Xenon has 8 valence electrons. Xe, surrounded by 8 dots, 2 on each side, is the electron dot structure. Radon has 8 valence electrons. The electron dot structure would be Rn, surrounded by 8 dots, 2 on each side. Now the goal of forming a chemical bond is for an atom to achieve a full valence shell of 8 electrons. Noble gases already have 8 valence electrons. Therefore, they are very unreactive. Hopefully you understand that the electron dot structures are the same for atoms of elements in the same group. How about electron dot structures across a period? Let's look at the elements in period 2, starting with lithium in group 1. By looking at our periodic table, we can see that all elements in group 1 have 1 valence electron. Start by writing the symbol, Li, and now add 1 dot to represent the 1 valence electron. I put my dot on the top, but feel free to place it on any side of the symbol. Beryllium is in group 2, and all elements in group 2 have 2 valence electrons. The electron dot structure for beryllium would be the symbol with 2 dots on different sides of the symbol. Boron occupies group 3 in period 2. The elements in group 3 have 3 valence electrons. You can create the electron dot structure for boron by placing 3 dots on different sides of the symbol B. I hope you are starting to see the pattern. Group 4 atoms like carbon will have a single dot on each side of the symbol to represent their 4 valence electrons. Nitrogen and all other group 5 elements will have 5 dots around their symbols, a pair of dots on one side and a single dot on each of the other 3. Remember to put a dot on each side of the symbol before pairing up the dots. Oxygen and the group 6 elements will need 6 dots around their symbols, a pair of dots on 2 sides and a single dot on the other 2 sides. Be sure to place a dot on each side of the symbol before doubling up. The electron dot structure for halogens like fluorine will consist of the symbol surrounded by 3 pairs of dots and 1 single dot, 7 valence electrons in total. We have already discussed the electron dot structure for noble gases like neon. 8 valence electrons, 4 pairs around the element symbol. Now we have discussed ions. We have even marked our periodic table for the ions that are formed by atoms in each group. But hopefully an electron dot structure helps you visualize the formation of ions a little bit better. Remember, 8 valence electrons is the goal. Would it make more sense for an alkali metal like lithium to lose this 1 valence electron or gain 7 more valence electrons? It's easier to lose 1 negative electron. That is why alkali metals form cations with a 1+ charge. It's easier for alkaline earth metals like beryllium to lose 2 electrons instead of gaining 6. Group 2 metals form 2+ cations after losing these 2 electrons. Lose 3 or gain 5. Losing 3 is a lot easier. Group 3 elements form 3+ cations after losing 3 electrons. Carbon could lose 4 electrons or gain 4 electrons. Well, that's the middle ground, so either is likely to happen. Group 4 elements could form 4- ions or 4+ ions. Now the tables turn. In order to achieve 8 valence electrons, is it easier for an atom like nitrogen to lose 5 electrons or gain 3 more? Gaining 3 is easier. Nitrogen and all other group 5 elements form 3- anions when they gain 3 electrons. Group 6 atoms like oxygen find it easier to gain 2 electrons than lose 6. Therefore, they form 2- anions after losing those 2 electrons. The halogens only need to gain 1 electron to achieve 8 valence electrons. That is much easier than losing 7 electrons. After a halogen gains 1 electron, it'll form a 1- anion. Noble gases have no reason to gain or lose electrons. They already have 8 valence electrons, and 8 is great. Noble gases do not form ions because they will not gain or lose any electrons. So what's the purpose of doing all of this? Well, in chemistry, we only care about the valence electrons because they are the only electrons that take part in chemical bonding. Electron dot structures allow us to visualize the only electrons that matter, the valence electrons. Now it's your turn. Use your amazing periodic table and the concepts you learned in this video to construct electron dot structures for these elements. This should be enough practice. So until next time.